covers everything from, as I say, sun to mud. And actually, I think that ignores the fact that there are planets with no mud that are part of the solar system that interact that are part of heliophysics. So every person in the field, including you, who are all in the field, studies a piece of this. And it's probably not practical to study everything at the same depth, but one of the things that is very valuable to you is to have an overview of the whole system, so you understand how all the pieces fit together. And then when you're doing your own part, you have a better idea of what context that occurs in. So, obviously the summer school is going to have lectures that cover all of this. We developed a couple of lectures that are meant to just start with that overview and not go into the same level of depth that the subsequent lecturers will do. And just so to give this overview, one of the things we thought up was, well, if you're studying the ionosphere, it's a natural question to ask someone why the sun or any other star has a corona, right? It's not your field of study, but if you don't even know why there's a corona, you're probably not going to be able to understand all the detailed physics of it. So we just set out these questions. Why are there magnetic fields? And as a way into the topic of understanding magnetic fields in stars and planets, and basically discuss some of the very basic physical problems that come up with that, or physical effects that we'll want to know about. So we're going to...
Dane,
yeah.
I'm sorry, they're recording, they're videotaping this. Could you use the mic?
Oh, do I have to put the mic on?
I think so, yes.
This is the third time they will videotape. You can go rank them, because I think they're also all posted. Sorry?
The slides will be, yes, the slides will be posted.
Yes. And you can also compare all the slides and see how little has changed. Let's see. I don't want me to turn this on somehow, right?
There's a
mic.
There's a button on the top.
Oh. How's that?
Yeah.
Is that easier to hear now? It's recorded for posterity. Yeah. Okay, so let's just get to it. But I'm just warning you. First of all, one of the reasons I'm going through this is the idea is that we should have enough fluency with this whole system that we should be able to answer these kinds of questions no matter what field you're in. And so none of these lectures apply to solar flares, which I've already told you is what I work on. So I am a rank amateur in every one of these topics. But please feel free to ask any questions. I can bluff my way through it. Maybe there's some expertise here. A lot of times the students will help me out. If that's your specialty, if you study the dynamo, then you know a lot more about the dynamo than I do. So you might be able to help me answer some questions. But I don't want to delve down into the very depths of that field, but just give people who don't work on the dynamo an idea of what are the basic issues at work. And so I'll do this with the dynamo, I'll do this with the corona, and then for my final trick, I will attempt to do it with the ionosphere and the magnetosphere. Okay, so, and you can see, I basically took it as an assignment to see if we have enough material in these textbooks to do this. So we assigned you reading from the textbooks. Trust me, they're good books because they taught me what I know about the dynamo. And you'll see what I know about the dynamo. Okay, so the question is, why planets and stars have magnetic fields? And here's some bits, cartoons, and images that are taken out of the book. And the answer, it's kind of not really an answer, but it introduces the new nomenclature, dynamos, right? The answer is dynamos. They all have dynamos. They all generate their own magnetic fields because of that. But what does that mean? It turns out a dynamo, as we'll talk about, is a way of sort of an electromagnetic process for generating magnetic fields. And there are three basic ingredients that we need in order to make a dynamo work. First of all, we need a fluid. Okay, let's see. Oh, neither of these is going to be very good. We need a fluid that is a good conductor, a good electrical conductor, because it's got to be an electromagnetic generator. Okay? We also have to have that fluid moving in some sort of complicated fashion. And finally, it actually has to move not only in complicated fashion, it has to be vigorous enough so that it can maintain this generation process. So, depending on what system you're looking at, the conducting fluid will be different. For stars, it's just a plasma, ionized plasma. For things like the Earth, which we all know has a magnetic field, it's not a plasma, it's a liquid iron interior. So we have liquid iron inside the Earth. That is a good enough conductor. We'll see. Vigorous enough is defined in terms of how good your conducting material is. For big gas giants like Jupiter and Saturn, they actually have metallic hydrogen on the interior. That's a very good conductor. And finally, some of the outer planets like Neptune and Uranus have more liquid water with ionized dissolved ions in it that will help them conduct. Basically, all of the complex motions we're going to talk about come about because the fluid's in turbulent motion, right? We have to have it swirling around or it's not going to do anything for us. It's often said that you need rotation, right, to help this work. It's not strictly true. You can have dynamos working without rotation, but they just tend to generate very small-scale random fields that don't do the kinds of things we often see. So that helps by breaking the mirror symmetry, you can generate a global magnetic field. And finally, you need this motion, this turbulent flows, to be vigorous enough. And the figure of merit here, and we'll come back to this, is something called the magnetic Reynolds number. I'll get the actual formula, but it's basically the velocity of the flows, the size, and the conductivity, the electrical conductivity. So if you have a poor conductor, then your magnetic Reynolds number might be low. However, velocity may help you. Things might move very fast. Actually, in a lot of things we're going to talk about, they don't move very fast. The liquid iron at the center of the Earth moves exceedingly slowly, right? Your little caterpillar would have no trouble beating it. But what always helps us when you're an astrophysicist or a space physicist is size. All of these things are big, much bigger than a caterpillar. They're a planet or a star, okay? You get those three things and you're going to get a magnetic field. I want to warm up with some basic physics. And this is what's known as a homopolar dynamo. It is not an astrophysical dynamo, but it has all the ingredients, sort of. And it's something that we can just use our basic freshman physics to understand how a dynamo works, okay? We have a metal disc. Sorry, the projector doesn't do this very justice, but this is just a disc. You can see it's a cartoon. It has an axle. It's going to spin on its axle. And it has a wire that goes around like this. It goes from the edge of the disc to the axle and basically makes an electrical connection there. So I said you need a conducting fluid. This isn't really a conducting fluid, but it is a multi-part conductor, right? I had two pieces at least. I have the disc and axle, and I have the wire. They're separate, and they cannot move together. Okay, so one of the things is they have to move separately. If I just welded this together and spun it, I would not generate a magnetic field. That's pretty obvious because I could go into a co-moving, co-rotating frame and I'd be watching this thing spontaneously generate magnetic fields just sitting there. That's magic, and that doesn't happen. So what really needs to happen for this is we do have to have two pieces of metal and they do have to move relative to one another. And this does actually have a lack of mirror symmetry. The wire goes around this way and therefore not the other way. Okay. Most importantly, for people who don't work on dynamos, people, very good, knowledgeable physicists I've realized have the misconception that somehow what you do to generate a magnetic field is basically take something charged and move it around, right? That would be a current. That's not what's happening. Nothing here is charged. Does everyone agree? We just have metals like you find everywhere, and if those were charged, we'd be in trouble, right? You touch them and you just get zapped. So there's no actual moving charges. There's no permanent magnets, right? This is not like what sticks your artwork to the refrigerator, and there's no batteries, okay? This is just, as I described it, a piece of, say, copper and then a copper wire. No charges. They do contain charges that are completely neutralized, so the electrons can move, in this case. That's how conductors carry charge around. Okay, any questions? Sorry, this is going to speed up pretty quickly, but let's just make sure we're all on the same page. So the first thing, which seems like I'm begging the question, is you have to have a magnetic field to generate a magnetic field, right? It's like the old principle about you have to have money to make money, right? You got to have a magnetic field. Now, it doesn't have to be very strong, but it's called the seed magnetic field. And I'm going to imagine it's going up here. And as I move this conductor, spin this conductor, it's got a V and a B, and it gives you what's known as an emotional EMF, or emotional electric field, E cross B. Okay, so in this case, because the magnetic field is going up and I'm spinning the wheel in the counterclockwise sense, I get an electric field that points from the axle to the rim. Okay, E cross B. V cross B, sorry. That means there's a voltage between the axle and the rim, and if I just integrate the electric field, that's like integrating VB dr, and I've just done some magic here. V is actually omega, the angular rotation rate, times the radius. I've integrated it. It actually comes out as two things that will have counterparts in astrophysics: the angular rotation rate, omega, and the net magnetic flux going through the disk. So I said there had to be some amount of magnetic field. Now we see what really matters for this voltage is the total area of the disk times that magnetic field strength, the flux. Okay? That is the voltage on the disk. Next, that voltage is going to drive a current. That's why I have this wire here. And somewhere in there, there's a resistance, R. And so the current times the resistance is equal to the total EMF around this circuit. That comes from this motional EMF and then what's known as the back EMF, right? Minus the self-inductance times the rate of change of the current. Sort of freshman level circuit type theory. I'm going to now invoke, okay, so we have the flux through the disk. I'm going to introduce the mutual inductance, right? L is the self-inductance, M is the mutual inductance between the wire and the disk, and so the flux through the disk is the current times that. Okay, so then I have this equation. I'm going to rearrange it, and basically I see that I have a current that's going to change in time, and there are two parts to its change. Both of them are proportional to I, so I just basically have a constant times I. The first part is this motional EMF. This is what's generating the current, right? We can think about this as a generator. It's actually generating a change in current. And the other one is the resistivity that's dissipating something, okay? So I just have a very simple circuit, and will the current grow exponentially in time or decrease exponentially in time? Simple first order linear ordinary differential equation. It will increase exponentially, always. It depends on gamma, right? When will it increase? If gamma is positive, it increases. So if the generation beats the dissipation, it increases. Yes, and there you have it. There's a solution. Basically, growth only occurs if gamma is positive. That it means omega has to be bigger than the ratio of resistance to mutual inductance. There you have it, my vigor, right? How fast do I have to turn this? It's set entirely by the resistance and the mutual inductance of the circuit. Once I've got that, someone will tell you, you better spin this thing faster than 3,000 RPM, and the current will just grow exponentially. That means I started with weak magnetic field. One thing about exponential growth, just like money, when it takes money to earn money, once you get that compound interest, it grows. And you will have a lot of current, a lot of magnetic field after so many E-foldings. So I don't really have to start with much magnetic field at all. Anything but 0 will do it. Okay. Now, omega was V over L. That we sort of started with. L is just a typical length scale. The resistance of any kind of resistor is just 1 over the conductivity times L. And basically the mutual inductance is just this magic constant mu naught times a length. Right? So if any of you want to know what your own self-inductance is, it is mu naught times your height. Right? You all pretty much have a microhenry of self-inductance because you all pretty much have the same height, at least to astrophysical levels. When you put all those together, this is what you get. You need this combination, mu naught, constant of nature, sort of, conductivity, size, and velocity to exceed 2 pi. That's the magnetic Reynolds number, the same thing I told you about. So even in this little toy, we still have the requirement that I need the magnetic Reynolds number to be above some threshold. If it's not, I will actually have exponentially decaying current. Okay, and we can make this by either making V big, making sigma big, or making L big. Have a really good conductor, should be possible. All right. Couple of things to note. If we basically started with field going downward, well, the EMF now is the opposite way. V cross B now points from the axle, from the rim to the axle, and it'll drive current in the opposite direction, which will amplify the opposite magnetic field. Exponential growth, both ways. It has 2 modes it can work in. It can amplify magnetic field going up or amplify magnetic field going down. Will it amplify magnetic field going left, right? No. So, 2 orientations you can generate this magnetic field in. If I put this in the mirror and also mirror my rotation, it will also amplify. You can try this out at home. But one thing it will not do is if I flip it in the mirror and try to rotate it in the same direction, now both terms will be negative and I'll always get exponential decay. All right. This sounds like magic, right? It sounds like I'm going to be able to generate infinite amount of magnetic field as the thing grows exponentially. Now, I have to sit here and turn this wheel. Okay, so there's probably some forces I have to fight against. Of course, everyone knows friction is a force that I'm going to have to reckon with. But let's say I put on some good bearings in here and made sure everything was lubricated well, so I'm going to ignore friction, right? We do that a lot. Is that it? Will I just be able to turn this thing? Because I'm going to turn it at the same rate forever and ever and ever. Or try. And the current will grow exponentially. The magnetic field will grow exponentially. But friction is not getting in my way. Any other forces I have to reckon with? Yeah, that's a good force. What? Induced by moving? Okay, let's see. Back there, did you? Lorentz force, I cross B, right? If you try to drive a current through a magnetic field, there's a force at right angles to those two. So I will get a force, if I goes this way, I will get a force that is I cross B, points in this direction, sort of backwards against the direction I'm turning. And you can see that if I is growing and B is growing, the force is growing. And I have to, in order to keep this thing turning at a constant rate, I'm going to have to use a bigger and bigger and bigger force. Okay? Actually, if I'm turning, the thing to work with is not the force, but the torque. F cross R, blah, blah, blah. You go through, you find out the torque is current times, again, the flux, which, if I use the mutual inductance, the torque is basically some constant times I squared. Just as we suspected, as this thing grows exponentially, the torque I need to fight is growing at an exponential that goes twice as fast. So the power that one needs to keep something going at a constant speed against a resisting torque is the rotation rate times the torque, and that is omega times I squared. So I actually have to do work to keep this thing moving at constant speed. That's kind of weird. Usually I only have to work if I accelerate something. But I have this force, this Lorentz force, fighting my motion. I also have ohmic losses. This thing's going to dissipate energy, heat up, due to the resistance. Okay, that's I squared R, one of the many ways of writing ohmic loss terms. If I subtract that off and say, okay, is that the only thing I'm doing is heating this up? No, you actually find you get gamma times the self-inductance times I squared. That is the rate, subtracting off the heating, that this is going up. And actually, you might recognize gamma times I is the time rate of change of I. So this is really the time rate of change of 1/2 Li squared. And 1/2 Li squared is the magnetic energy stored in a self-inductor. Okay, that is the magnetic energy. So I have to do work for two reasons. I have to do work because some of it's being lost to heating, and I have to do work because as the magnetic field gets greater and greater, it's storing energy. Where did that energy come from? It came from the croissant breakfast I ate this morning. Okay? It comes from me, and I have to supply that energy. When I run out of breakfast, I'm not going to be able to keep going at that same rate. My rate will slow down, omega will slow down, gamma will decrease until it gets to 0, and then I will have just the same amount of force that I can withstand, and my dynamo will do something we call saturating. So in this toy dynamo, we have something that will exponentially grow until I run out of juice, and then it will saturate, and the magnetic field strength will reach some maximum, or the current will reach some maximum that's dictated basically by my ability to overcome all of the Lorentz force, really, and the ohmic dissipation. So that's the toy. Here's reality. Many of you talked about working with MHD, so you might recognize the equations of MHD here. Mass continuity, we'll hear much more about this. This is the momentum equation. This is the energy equation, or a version of the energy equation for a nice conducting plasma. This would not apply to the liquid metal in the core of the Earth exactly. I think we'd have to be a little more careful with our specific heats, but basically it gives you the flavor for this. And then there's what's known as the induction equation. This is basically all the stuff we had in that toy model. Well, it's a lot more, but here is J cross B. This is the Lorentz force that was so important in saturating my dynamo. Here is the ohmic heating that was also being accounted for. And here is the induction equation. This is basically the V cross B, the motional EMF. So if you haven't seen these before, you'll have time to see them again. One of the things you can do, though, is to take this equation here, take this term in particular, and write it so it looks like a diffusion of magnetic field, just this term here. And so this ends up looking like something is actually trying to allow the magnetic field to diffuse. One of the other ways you can do this is to use a vector identity on this term here. You look up your table of vector identities, and you basically have a time derivative of B in the frame moving with the fluid, and then you have some other terms with B that we're going to get to, and this dissipation. Okay, so this is much more complicated. However, there is a scenario we can think of that's a little easier to work with. Imagine that we haven't reached the point where the Lorentz force, the back reaction of the magnetic field on the fluid, matters, and the ohmic dissipation doesn't matter. In that case, we can get rid of those two terms, and what we're left with is no longer MHD, this is just HD. This is just the equations for motion of a fluid like the air or the water, something like that, no magnetic field involved. So presumably you can solve that. That's also very hard. But once you solve it, you will find the velocity of this fluid. And the velocity will be something that you put into this equation here. And if you know the velocity, then this is an equation that's linear in what you don't know. B, 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 and B. Okay, so once you've got V through the simple procedure of solving Navier-Stokes equation, then you will be able to figure out if B increases, decreases. Okay? And in fact, as I said, this first term here is the time rate of change of B if I move with the fluid. This weird-looking term here is nothing but a matrix dotted into B, and then we have a diffusion of B. So we have a matrix, B dot a matrix, and it's a 3 by 3 matrix, yes. If I didn't have any dissipation, what would happen? Well, what would happen depends on, of course, the eigenvalues of the matrix. If that matrix has one positive eigenvalue, okay, then there will be a positive eigendirection in which the magnetic field grows exponentially in time, just like in our toy model. Okay? There's a reason I do the toy model. It sort of looks like something you should be able to do, and it is pretty simple physics. And then MHD has the same kinds of answers. Exponential growth for the magnetic field, providing the magnetic field, this matrix, which involves only the velocity that I supposedly figured out. And in fact, if you include the dissipation, my growth rate is the velocity divided by L. That's one of the eigenvalues of that matrix. And then eta over L squared, that comes from eta del squared, eta over L squared. And that's basically V over L times this constant here. And I'm going to get exponential growth if this number here is less than 1, or if I turn it upside down, LV over eta is greater than 1, and that is the same as the magnetic Reynolds number. So it has the same exact behavior as that little toy model. If I have a velocity field that is vigorous enough, it's going to cause magnetic fields to grow exponentially. And how vigorous it has to be depends on the conductivity of the plasma, the size scale. Right? So if I have a big thing like a star, I'm doing much better than if I try to do this in something I can build in my garage. And it has some of the other properties. I won't go through them. But then you say, but what about this eigenvalue? How do I know if the eigenvalue is going to be positive or negative? Well, you can look at what this matrix actually looks like. And here's what the matrix looks like in a simple two-dimensional case. And I've shown a sort of flow that all converges along the y-axis and diverges along the x-axis. And that's what the matrix looks like. I've actually worked it out. And it basically has a 1 and a minus 1 on the diagonal. The 1 is the thing that matters. I said any positive eigenvalue will do it for you. So apparently that's the one that matters. And what it tells me is if I have magnetic field that's oriented along the x direction, or if there's any component along the x direction, this flow will amplify that magnetic field. That magnetic field will grow exponentially. The only way to get out of this is to have the magnetic field pointing exactly in the y direction, perfectly, no errors. And if anyone ever tells you you can do that with no errors, they're lying to you, right? There's always going to be some little bit of wobble that will give us an x component to the magnetic field, and our dynamo will feed off that. We'll amplify it exponentially. Exponential growth will win every time. That's right, and Rika, unfortunately, was sick a couple days ago. You were probably had a couple of little virus particles in you, They grew exponentially and they took you down. Sorry to report that to everyone, but that just shows you it doesn't matter that you had all this other stuff that wasn't a virus, right? That never matters. It's the viruses that get you, okay? So it's the exponential growth that's always going to dominate. Of course, with, well, viruses, you just have to wait them out. Bacteria, you can take antibiotics and that'll give you advantage. Okay, let's not get sidetracked here. So what this actually does is takes the magnetic field that's in the x direction and essentially sweeps it and compresses it. There's ways of thinking about this, but I just want to focus on the fact that I have a positive eigenvalue and the eigenvector is the x direction. So actually, one of the ways to think about this is stretching the magnetic field lines. And the reason that it's useful to think of it that way is if I took a little blob of paint and put it in this flow, and it was circular to start with, the flow would stretch that blob of paint until it was long and thin. Does everyone see that? So I take this, and basically it squishes the paint in the y direction and stretches the little paint blob in the x direction. So essentially, any flow that would mix up blobs of paint has a positive eigenvalue and will amplify magnetic fields. Now, does it sound pretty unlikely that you can generate a flow that doesn't look like this, but that would mix up paint? Anyone think that that's hard to do? Or how about cream in some kind of hot beverage you might have? Is it hard to mix that up? Did you have to spend years studying how to do that? Well, you stir it, but what's more important than the stirring part? What do you do when you stir coffee? You create turbulent flows. Intrinsically, you didn't study how to do it, but just the fluid itself will become turbulent when you stir it. That will mix up the paint. If it were a good enough conductor or a big enough cup of coffee, it would also amplify magnetic fields. Same thing, okay? So basically, that's it. All you need to amplify magnetic fields is some kind of fluid that has good enough conductivity that its magnetic Reynolds number will be big. You need to make it swirl around so that it has a positive direction to amplify magnetic field, and you're good to go. So, turbulent flows will work. Now, we could go into detail, and we'll talk more about turbulence. Turbulence is an interesting topic all by itself to study. There's a second dimensionless quantity known as the Reynolds number, the vanilla plain old Reynolds number, that is very similar. It has to do with the size, the velocity, and the viscosity instead of the resistivity down there. If that's big enough, any flow you have is turbulent. I'm sure there are exceptions to that rule, but that's been my rule. Viscosity in coffee is extremely small. So it's impossible for you as a human being to stir this and not make it turbulent. If you were a microscopic coffee-loving microbe, you probably could do laminar flows. So turbulence is not hard to achieve, but you do have to be bigger, have a large Reynolds number to do it. Okay? And finally, remember, the turbulent flows amplify magnetic fields in every direction. If you have rotation, that's going to organize your turbulence. It's going to give it a direction of rotation that it's going to line the eddies up. And what that will do is they will sort of amplify in a more coherent, I'm not going to say coherent, but it will basically give them a direction that they will want to amplify. But you only need rotation, but you need the rotation to affect the turbulence. Okay? And there's a criteria for that known as the Rossby number. And let's see, we have at least 2 people here from the southern hemisphere. I'm not seeing, yeah. So, toilets, flushing. Do they go the other way in the southern hemisphere? No, they don't. Well, they don't always. What you need is you need the rotation rate, omega, to be bigger than, or in other words, the period of rotation to be shorter than the period on which it takes one of these eddies to swirl around. So, if the rotation of the Earth once every 24 hours is affecting your toilet, then your toilet is taking more than 24 hours to flush, and I suggest you call someone about that. Now, hurricanes are a different matter. It takes them days to completely cycle. So to them, the Earth's rotation is very significant. It happens very rapidly if you're a hurricane, and your hurricanes go around one way in the northern hemisphere, the other, because the Rossby number is small for hurricanes, and it should not, under good circumstances, be small for a toilet. Okay, so rotation doesn't matter for small things like that. L is small. That'll make Rossby number big. Okay, and the velocity, again, toilet velocity should be fairly large enough to get the stuff out in under 24 hours. Okay, well, so in order to organize the magnetic field, we need a small Rossby number, a large Reynolds number, and a large magnetic Reynolds number. Here are two examples. And I'll just focus you on the sun, made of plasma, is a very good conductor. The magnetic Reynolds number is 10 to the 8. We need it to be bigger than 1. We win. This is big. The actual Reynolds number is even bigger than that. So the turbulence is going to be very vigorous. Okay? The Rossby number, yeah, it's smaller than 1, but not by a whole lot. That means it's not going to be super good at organizing this magnetic field, but it will manage to do that. The core of the Earth, as I said, liquid iron is not such a great conductor. So our magnetic Reynolds number is only 100. But it just needs to be bigger than 1, so we're okay. The Earth is rotating much faster than the sun, but it is smaller, and the velocity of these motions are actually very small too. So altogether, that gives us a pretty good, Rossby number, 10 to the minus 6. So even though it takes these, well, what happens is it takes these eddies inside the Earth thousands and thousands of years to turn over once. And it takes the Earth 24 hours, or 23 hours and 56 minutes to be precise, to rotate once. So it's winning. It rotates many, many times for one of those turnovers, and the Reynolds number is pretty good. So both of these cases pass all of the tests, and they do generate magnetic fields. And we know about one of those magnetic fields, and probably some of you, a lot of you know about the others. So let me just review this. So we've sort of seen that we need these ingredients. The electrical conductor, we need complex motions, turbulence. We need to make at least one positive eigenvalue. That's the one that's going to dominate. If we get rotation, then that's going to probably, all the eigenvectors will be able to line up based on that, and you'll get a large-scale magnetic field instead of a lot of small patches of magnetic field. And we do need this large magnetic Reynolds number in order to get that. I think I will give us a little bit of a break here. Are there any questions before we just take a sort of 3-4 minute break to stretch our legs? Any questions on what we've done so far? I know the MHD went up in a hurry. We're going to see more of it, but I wanted to show you what we've used, and it really has a lot of basis in the basic physics you learned as a freshman, that you have magnetic fields, and you have motion, and you have currents. Remember, nothing involved taking charged stuff and moving it around. Nothing was charged. Yeah, question? No? Uh-huh. Oh, that's, yeah. So you want to know, in this picture here, what is happening to create this stronger and stronger magnetic field? It seems like there should be currents involved somewhere. Is that what you're worried about? Well, I guess we could talk about that at length, but I sort of threw this at you This is the electric field as experienced by the conductor. It has two pieces. One is Ohm's law. Ohm's law turns out not to be that important. And the other is this motional EMF piece. Ohm's law involves current. The motional EMF piece does not. So the tricky thing the way to trick you into believing all this is to say, actually then, I can have this equation for how the magnetic field changes that has nothing to say about currents. Now, it doesn't really have nothing to say about currents, because once I find the magnetic field, I can take the curl. But the weird thing is this magnetic field doesn't seem to have any current. So it looks as if there's no current. Probably this is one of those cases where you have to go outside of the system and the currents live there. And the thing is, that just shows you when you're going to solve problems, it's always best to pick up the right tool to solve the problem. And in this case, currents are not the right tool to solve the problem. So although some well-meaning person may have told you that magnetic fields are generated by currents, currents create magnetic field, this equation shows you that that's not exactly the case. That the magnetic field can just sort of be there and change under the influence of the flow of a very good conductor. And that's just the way it is. You can actually go back and try to unravel this all. If you insist on understanding how it all relates to currents, you could also go back and try to figure out your parking ticket based on the origin of Justinian law in the Roman Empire. Neither is a very fruitful exercise. It might be intellectually pleasing, but it's not going to get you very far, and you're not getting out of your parking ticket that way. Yeah. Yes. We're going to talk about all the planets in detail, but let's take a break first. Yeah, that's a good, but yeah, let's talk about that. That's a good question, but I'm going to beg off. Okay, let's take 3 or 4 minutes, come back. We can start talking about the details. Or you can sit there and just leave the slide or leave. Here he is. All right, is this better? Is this? I don't know if it's better for us. I think most people can hear me in a room this size. All right. Yeah, it ran out of batteries. I wished I had a green laser pointer. Oh, you have replacement batteries. I have replacement batteries for my noise-canceling headphones, but I'm not going to donate them to HAL. Yeah, good. Slider ramp. Generally goes a lot faster. Oh, shoot. Just some small number. I heard. Do you want this higher? This, okay. Okay. Good. Yep. Yes. Yes. We have. Yeah. We have a good, reasonably good prep run. I might ask him to tweak it, but yeah, it actually. Yeah. Yeah.
been writing, I've been reading. It's already like 5 papers on this event. Yeah, but the ones we have, the emission measures and the temperatures, the emission measure does not increase nearly as much as I was hoping. In the data, it seems to, it seems to change by like 3 orders of magnitude. No, the emission measure. And the temperature changes only by like 25%. Along with, and so in the Preft, even with the effect of the magnetic field, the emission measure, at least I'm going to make sure I'm doing all this right, seems to go up by an order of magnitude, not 3. And the temperature goes more or less up by a factor of 4, not 25%. Yeah, well, I think so. Yeah, it is. And it's greener. I've been told by several people that red somehow is, our receptors for red are not nearly as good as our receptors for blue. So, spotting things in red is not a good idea. Making a laser photo in red is not a good idea.
It's such an aggressive color.
Okay, so that was the physics and math intensive portion of this. I wanted to get into the solar system, and we started out by just testing that yes, all of these ideas about magnetic Reynolds numbers and Reynolds numbers appear to apply. Let's take a look first at the Earth's magnetic field, because we might be sort of more familiar with that. And one of the things I want to point out is we have a bunch of different pieces of the Earth. We have this mantle up here, which is not a liquid and is not a very good conductor. In fact, it's such a poor conductor that we can pretty much say that within this portion of the Earth, the current is 0, so curl of B is 0. And if you have a field with no curl, you could write it as the gradient of a scalar, known as a potential. So this is sometimes called the potential magnetic field. B is minus grad chi. And then if I insist that B be divergence free, I find out that chi is harmonic. Its Laplacian vanishes. Okay? So that's going to come in handy in a second. Down here is the place where we have a liquid. It's the outer core. Sorry, there's an inner core that is actually solid. And the inner core is, the outer core is liquid, and it's iron with some other light elements like silicon. The solid piece is just the iron. So what's happening is the iron is precipitating out because the Earth is cooling, and it leaves behind extra light elements down at the boundary, and that wants to float to the surface. So that's what's driving all of this complicated turbulent motion, which we know is ingredient number 2 in our list of ingredients. It is a reasonably good conductor. As we saw, the magnetic Reynolds number isn't super big, but it's good enough for what we need it to do. And so it's going to generate a magnetic field. Now, for the outer portion, where the magnetic field is actually current-free, I know, and all of you, I'm sure many of you, most of you, know how to solve Laplace's equation many, many different ways. In spherical coordinates, we use spherical harmonics. These are these wonderful functions, YLM, that depend only on theta and phi, and then a radial dependence that goes as L plus 1. So you have this complicated function, and then the magnetic potential falls off inversely with distance, and the higher the value of L, the faster it falls off. Okay, and so if you actually look at the magnetic field, it's just the gradient of this that's also going to fall off. this is just the pictorial representation. If L is equal to 1, that is a dipole. There are 3 versions of that. Basically, a dipole can point in 3 directions. That is the dipole moment. It's just 3 of the terms in this infinite series. So when people say the Earth has a dipole field, you say yes, but it has all these other terms. L equals 2, that's the quadrupole field. Here are some of the L equals 2 spherical harmonics plotted in color. Higher L's, here's L equals 5. There's a bunch of them. If I have a general solution to this equation, it has all the L's in it. Okay? And the Earth itself has all the L's in its magnetic field, and they fall off with distance. So if I look at the magnetic field down here where it's being generated, actually, this is a plot of the power in the magnetic field, and I don't want to go into all the details about how this works, but we're basically just plotting the coefficients in this expansion as a function of L. The geophysicists seem to call it N. And some of this comes about from trying to extrapolate what this is, and that comes about from things that don't come from the dynamo but come from other sources. So let's just look at these low areas. It looks like all of the L's, all of the power is very similar. The dipole is a little stronger, but other than that, they're all about the same. That's because it's a magnetic field generated by turbulence, right? So there's no L that it says is more important than the others, possibly except L equals 1. But it's all very similar looking. Now that's down here, where the magnetic field is generated. If I go up to the surface where I live, there's a hot spot. There's the big island of Hawaii, which is actually erupting. Kilauea is erupting right now. We're at a larger distance, and the magnetic field is going to fall off with L. So by the time you sit on the surface of the Earth, it definitely looks like the dipole moment is the strongest contribution. But that's not because the Earth has a dipole magnet in it. It's because we are a long way away from this very complicated magnetic field that it's generating. Okay? But it falls off. So here is a plot of just BR on the Earth. So there are places where it's negative, like up here in North America, in Alaska. Places where it's positive, like down here in Africa or out in the South Atlantic, etc. Well, this looks really complicated, right? This is not the magnetic field that you would be able to use your compass on. What's the issue here? This is at 0.55 of the Earth's radius. This is what the magnetic field looks like down there. If we actually, so here is a cartoony depiction of the Earth. The light gray is the mantle, the dark gray is the liquid core. That shows you where we're making a map of the magnetic field. And if we, and I don't know how to do this, but if we move, and you'll see that black region, which is where we're plotting it, moves outward, and the magnetic field gets much simpler. So by the time you get to the surface, or this is actually slightly above the surface, it looks like all the magnetic field is pointing into the northern hemisphere and out of the southern hemisphere, as if it were a big dipole, right? But that's just the artifact of being so far away from where the magnetic field is actually generating. Another thing you'll notice is this is what the magnetic field in that portrayal, actually at the surface, looked like in the year 1800. And then over time, we actually see it change. And why shouldn't it? It's being generated by a turbulent flows inside of the Earth. So nothing is steady about turbulence. It's just constantly swirling around, constantly changing the magnetic field. We see even the dipole moment. But of course, if we look at the magnetic field at the base of the convection zone, at the top of the outer core, it looks complicated, and you can see it changes much more dramatically because that's really where the turbulence is generating this magnetic field. Okay, and in fact, just an exercise, and this is in the textbook, you can actually work out what the flow is. If you just make some approximations to this equation here, you're actually seeing the changing B, right? So now we've turned around from saying, conceptually, I thought I knew what the velocity was going to do because I knew how fluids behaved. Now you're going to say, I've observed the changing magnetic field, so I know dB dt, I know B, and I can solve for V. And here's what, at least at the top of the core, the flow pattern looks like. It's moving around, and I think it is fairly slow, sort of, what's that, 1/3 of a millimeter per second? Not very fast. Right? V is very small, but yet the magnetic Reynolds number is big. We have two things going on for us. One is that, well, resistivity really doesn't go for us. We just have size. The Earth is really big. So even though the flows are very small, the Earth is big enough to make this a working dynamo. And one of the consequences, I know many of you work on space data. Over the last 100 years, we've had a little place of opposing polarity move its way into the South Atlantic, which has created the South Atlantic anomaly, which has consequences for spacecraft. Almost deprived us of our gamma ray observations of the neutron-star merger. Some very, very foresightful person decided to keep Fermi on just a few minutes into the South Atlantic anomaly, and we caught it. All right, but it's not a static magnetic field, and in fact, it flips back and forth. And here's an old plot of that. Basically, the black is the place where the magnetic field goes from the southern hemisphere to the northern hemisphere. We like to call that the normal orientation. But you saw in the toy dynamo that a dynamo will generate magnetic fields in two orientations. It doesn't care. It's completely agnostic to which orientation it generates the magnetic field. It doesn't have to change its flow at all. And the Earth is just such a thing. It will generate magnetic field in the normal configuration or the reversed. Magnetic field going from the northern hemisphere to the southern hemisphere. And over millions of years, this is 5 million, 10 million, 15 million years ago, all the way back to 120 million years ago. Some of this may really come from the resolution with which this data is obtained. I'm not sure that people believe that the Earth's magnetic field was flipping back and forth less frequently back then. But it flips periodically, okay? I shouldn't say periodically, sporadically, right? This is not a periodic function. This is black, white. It looks like a barcode. Okay, so that's perfectly natural, right? Why shouldn't it flip back and forth? It can work in two modes, and it's driven by a chaotic random process, so it just seems to kick itself into the other mode once in a while. Let's now get to some of our outer planets. We've already talked about what dynamos that do work have going for them. Mercury, well, let's not even talk about that. Venus does have a liquid iron core. The real problem appears to be that Venus doesn't have enough turbulence in its core to generate the magnetic field. Its core seems to just be sitting there, like chewing nougat in a Tootsie Pop. So no swirling motion, no magnetic field. Mars, I don't think doesn't even have a liquid core anymore. So none of the ingredients, no magnetic field. Moon, no magnetic field. Jupiter, Saturn, we have this metallic hydrogen or helium, very good conductor. They're actually have, I think, radioactive decay driving turbulence in this stuff. So lots of turbulence to go along with it, and also good rotation. Uranus and Neptune actually have this slushy liquid here that is a reasonably good conductor. They're also very big planets, so we have that going on our side. So this is where our magnetic fields are being generated, by and large. Here is a sort of a discussion of how how these things have magnetic fields. Here we see what was alluded to. Well, we'll see it actually even better here. This is a similar plot to the ones I showed you for Jupiter, for Saturn, for Neptune. Mars, does this look like it's being generated? No. This looks like a bunch of rocks got magnetized at some point in the distant past, and it's just stuck with this magnetic field. So these three are generating their magnetic field. Saturn has a very smooth, symmetric magnetic field. I don't think there's a lot of understanding of why that is. The arguments I've mostly heard against it are just luck of the draw. How likely is it that the dipole moments, remember, it's just three numbers that tell you what the dipole field is going to look like. And then all the quadrupole, octupole fields tell you how distorted it's going to be. So the fact that it lines up with a 0-degree tilt, right, dipole tilt, the dipole tilt is just telling you about those three numbers. So somehow, two of the numbers are very close to 0 for Saturn. Jupiter, not so much. Neptune, definitely not. But this is just, in the big picture scheme of things, it's just the kind of thing that you expect. If you have these ingredients, you're going to generate a magnetic field, and the magnetic field is going to be complex because it's being generated by turbulence. And if you're far away from it, it's going to look fairly dipolar. But should it be perfectly aligned? No. Right? Sorry, so I can't answer your question, but it is a topic of much discussion. This is just a little bit more, and this is actually in the books. Stanley talking about it. And these are the ice giants, Uranus and Neptune. You can see Uranus has a magnetic field that almost doesn't even seem to have dominated by a dipole. So I think a dipole at a very strong angle. The final thing I was going to point out, because I talked about the way the magnetic field is amplified by the turbulent motions, and it's amplified up to a point that the flows can no longer sustain the motion, or they can't sustain the motion in a way that will continue to stretch the magnetic fields. The magnetic fields basically have to turn into a direction where they're not being stretched anymore, otherwise they shut down the flows. Okay, so once the thermal conduction, which is the thing that's driving the turbulence, basically the heat trying to move its way, or light material trying to move its way from the inside to the outside, balances the ohmic dissipation, that's when you expect this saturation to occur. And here from the book is just sort of the plots of the different planets we have. And Saturn, again, seems to be somewhat weird unless you monkey with where its core mantle boundary is. If you put it there, you do find that, yes, you can predict how strong this magnetic field is going to be. Jupiter's magnetic field, very strong because it has going for it this very strong thermal conduction, as well as, some very strong thermal conduction balancing it. But we sort of understand then why the magnetic fields of the different planets are the size they are. It just doesn't have to do with this generation mechanism. It has to do with when that generation saturates. Okay, so that is, and as I said, I'm not an expert on planets by any stretch of the imagination, but this is sort of the picture you want to have going in before you hear more details of planets. They generate magnetic fields, why, how they saturate, things like that. Any questions on that? Before we move on to stars. Our favorite star, the sun. Story is as all the same ingredients, right? It's a conductor. It's a liquid conductor. That is, it's made of hydrogen, helium, plasma. Almost all, except for a thin layer on the outside, is fully ionized. There is turbulence causing the outer 1/3 of the sun to be convective. And I showed you before the Reynolds number for this outer fluid is 10 to the 10, so of course it's going to be turbulent. It is a good conductor. The magnetic Reynolds number is 10 to the 8, so a very good conductor. Its rotation is so-so. Right? It's rotating once every 25 to 30 days, depending where you go. And the convective turnover time is comparable to that, depending on how deep down you go. So you have sort of a 100-to-1 disparity between those. So the rotation does give a preference to the direction the magnetic field is generated. Up higher, things move faster, and we're back into the toilet bowl regime. The very surface of the solar convection zone is not being influenced by rotation, and it's generating magnetic field. It's generating magnetic field. We see lots of magnetic field. It's just not organized. So you'll see this disorganized magnetic field, and you'll see a picture of it in a second. The term of art for it is salt and pepper. We tend to color code it white and black, and it basically looks like it's just spewed all over the place, white and black. The deeper convection is slower, therefore more dominated by rotation, and that generates the large-scale magnetic field that's organized. So here you see what I'm talking about. This is a white light image. These are the sunspots. Around the sunspots you see regions. If you haven't seen one of these maps before, this is a map of the solar magnetic field. Black is magnetic field that's going into the page, and white is magnetic field that's going out of the page towards you. This is not done using magnetic field measurements in all three components, just that one component. So you do have a little bit of projection effects. This is coming out of the page and therefore mostly out of the sun, but there's also definitely a westward component to that field, an eastward component to that field. But anyway, you still get to see the positive, negative, negative, positive, positive, negative, positive, negative, and all of this salt and pepper, some of which is just left over from organized magnetic fields that were emerged, but a lot of it is just generated by this layer that doesn't have anything, doesn't have any knowledge the sun is rotating. It's swirling around too fast. And so that's just giving us, it generates a magnetic field, it's just not organized. The sort of explanation for why we see organized east-west and west-east fields is that the magnetic field is generated by and large in the east-west direction and the west-east direction. In fact, it goes this way in the northern hemisphere and this way in the southern hemisphere, and that magnetic field actually pokes up through the surface of the sun and gives rise to, where it pokes up, you'll see an outward magnetic field, back in, an inward magnetic field. It goes the opposite direction in the southern hemisphere, so it's inward and outward, outward and inward. Okay? So this is just, without going into lots of details about how these dynamos work, it's all the ingredients I told you needed to have. You need to have this turbulence swirling around, and it does that in the outer one-third of the sun, and then the rotation of the sun is giving rise to a preferred direction, and that preferred direction is east-west, and that's stretching out the magnetic field, or making the magnetic field preferentially go that way and that way in the other hemisphere. Okay. One way we'll often plot these is we take the entire sun and just extract the magnetic field from right down the middle of it, we call the central meridian, and then on a given day we paste that in and we wait for the sun to rotate, and we paste in the next day and the day after that and the day after that. After a full rotation, after 29 days, we have a full map of the whole surface of the sun, except maybe the poles. Depending on the season, they're tilted away or towards us. But in these latitudes, we have a pretty good map of the sun. So we have our places with outward, inward, outward, inward. You can sort of see some of these patterns. Up in the northern hemisphere, it's negative, positive. the southern hemisphere, it's positive, negative. Okay? And the reason I show that is really to bring this back and say, so is the sun's magnetic field that different from the Earth's magnetic field? Well, if I plot them both in this kind of map, I'm not sure to the untrained eye how easy it is to tell them apart. You do see a slight preference in the Earth for a dipole. Remember, the dipole moment was a little bit stronger on the Earth, and that has to do with subtleties of how this large Rossby number interacts with the magnetic field. The sun, a much smaller Rossby number. The Earth's Reynolds number, magnetic Reynolds number, is low. The sun's is high. But otherwise, we've got a dynamo, and we've got a dynamo. Okay. Obviously, the units are going to be different. This, again, is plotting only the magnetic field at the place where it's being generated down at the top of the core. And this is also the top of where it's being generated, in other words, the surface of the sun that we see. Because the sun's magnetic field is generated in a layer outside, and the Earth's magnetic field is generated by a layer inside. So that's probably where you get the idea that these are two very different kinds of things going on, because we don't live inside the Earth, and the sun doesn't generate its magnetic field inside the sun. It generates it on the outside. Okay. Question? Yeah. Okay. Yep. So the, right. So, that's a good question. So she's referring to the fact that in some, but not all, ideas about how the sun's magnetic field works, a majority of the generation goes on right at this interface between where the fluid is convecting and where it's not. And that's also referred to as the tachocline. It also involves a change in its rotation. It's more rigid rotation down here. So the sun has a magnetic field. Now, of course, we're going to get to stars, and there are cool stars where the convection zone is very, very deep. In fact, stars that are cool enough that the whole thing is a convection zone. It has no tachocline. Those things generate wicked strong magnetic fields. So that's one of the reasons people often go in and say, maybe this idea of the tachocline being so important is not exactly true. Now, what is true is the deeper you go, the larger the smaller the Rossby number, the more it's dominated by rotation. So the largest scale fields have to originate deeper down. But the stuff that originates up higher is just not going to be as organized, and it's going to look like all that salt and pepper. But I'm not sure that doesn't answer your question. I don't know the role of that interface layer in the Earth's dynamo. But that's an interesting point of speculation. Yeah.
Thursday morning.
Thursday morning. Okay, good. So yes, that's a time to raise a question like that. I was gonna touch back on our yeah. Oh, question. Yeah. Yeah. No, it's not frozen in. Frozen in would be an infinite conductivity, and therefore an infinite Reynolds number. So this is actually, this idea, this isn't assuming anything, by the way. This is just a map of what it was on May 19th of 2001. I don't know why I chose that day. But when you do work with models, having a finite magnetic Reynolds number means you are assuming resistivity, and the field is actually sliding through the plasma.
That actually turns out to be a crucial part of making these dynamos work. If you don't have resistivity, it's very hard to make them work. Yeah. Any other questions? Or we just go on to solve Laplace's equation again. Just doing this to lead into our lecture this afternoon, which is going to discuss the solar wind. If we have this complicated magnetic field, as we have here, then what happens above it? And one of the simplest things we can think, and the motivation for this is, well, the region above it is this million-degree plasma. It seems like it would be really good at carrying currents. But it also has very little stuff. So there's a limit to how much current it's going to want to carry. And so a common assumption is to say, well, let's imagine it doesn't carry any current, and we're back to a magnetic field that has zero curl. I can write it with a potential, and I can solve Laplace's equation using my spherical harmonics. And that is what is often done. It's known as a potential field source surface model. And this is a picture of some of the field lines coming out of, and so you see these regions of positive and negative, outward and inward field, and magnetic field lines that come out of them are being created by assuming there's no current above the surface there. This is a potential field model. It's not 100% accurate, but it's a very common tool, and I believe, Nick, in at least one of our labs, if not more, we see these PFSS models being used to figure out what the magnetic field looks like on the outside of this complicated dynamo here. So this is what a magnetic field looks like in this synoptic plot at the solar surface, right? I told you how we build this up. If I go out 2.5 solar radii and look at what happens to the magnetic field, well, we've already observed that the lower the L value, the slower the magnetic field contribution falls off, and you eventually get to a place where it looks much more like a dipole. So even though this hardly looks like a dipole, the field at 2.5 solar radii, this blue is all outward field, and this gray is all inward field. I believe that's right. And you would have been hard-pressed to say that this had a dipole moment, but it obviously does. And this is the orientation of that dipole. And it really just has to do with the spherical harmonic decomposition and what that L equals 1 contribution was. Here I'll show you how this evolves. We've already observed that the Earth's magnetic field reverses every 300,000 years, almost at random. Oops. See if I can get this one to go. This is, I think, 11 years or more. And you can see it gets very squiggly. The dipole moment has sort of died away, and we're dominated by quadrupole. And then the dipole moment returns, and it's oriented the other way. So we started out with gray on the bottom, white on the top, and we end up with white on the bottom, gray on the top. So the magnetic field is flipped over. Well, that's one way to say it. Those three numbers, the dipole moment numbers, have become small and then become large again. And that's really what's happening as the sun's magnetic field is being changed by the turbulence generating it. This is a plot of, in blue and red, just the upward component of that dipole moment. Okay, so it is pointed northward, and it crosses 0, and it's pointed southward, and this is just one number. So of course it can cross 0. For a vector to cross 0, it's kind of rare. Right? Its whole magnitude has to go. That's 3 things have to go to 0 at once. That's like having 3 cats and expecting them all to do the same thing. They're not going to do the same thing. Cats just don't work that way. But this one is going to go positive to positive again to negative over, this is 1975 up to 2010 when I made this. The green is the magnitude of this dipole moment. You can see at periods, the magnitude and the z component are very similar.
it's mostly oriented in the z direction. The Coriolis effect, or the rotation, has that preferred direction, and that's what's organizing the magnetic field, so it tends to be oriented in that direction. You'll notice the green never goes to 0. The dipole field never goes to 0. But it does get weak. And it's at that point when it's weak, right, down here, when it's weak, that, wow, what do you see here? You see positive, negative, positive, negative. And then basically this is the same positive as that. So positive, negative, positive, negative. Is that a dipole? That's a quadrupole. Yeah. Just that the dipole moment is small, but the quadrupole moment is still there. So this is sort of the intermediate phase of that. Here's the dipole, where the dipole moment is dominant, and it's north-south oriented, just negative, positive. Okay? So the large-scale behavior of this magnetic field isn't that hard to understand. Down here, I've also plotted the sunspot number. That's just literally what it sounds like, counting up the number of sunspots. That's been done for a long time. We have records that go back. Well, this only plots back to the map. I think we might be able, Nick, have we, in the past, we've been able to get upstairs and see the original plots that were being made by Maunder, plotting out, and then he was the first one to recognize that it had this pattern. Not only that it was alternating north positive, or he didn't see that it was alternating positive, negative, but he did see that it was going high, low, and also that if you plotted the latitudes of where you saw sunspots, they came from relatively high latitudes, not much above 30 degrees, definitely not above 40, and then over the course of time got progressively closer to the equator. And this is just the count. This is the thing that you would notice just counting them up. This is if you plot their latitudes. So there's a sort of a rich behavior to the way this works. Here's adding in, instead of the actual just sunspots, this is sort of extracting a synoptic map per month and then lining them all up. And you can see the butterflies. Of course, this is only from 1975 when we had this kind of data. You'll see that the magnetic field of one sign and the magnetic field of the other, here it's done as blue and yellow, and the butterflies, and then the appearance of magnetic fields close to the poles. That's just a byproduct of this, having to have this large-scale field dominated by the dipole. Let's just skip over that because we're going to start thinking not only in terms of our solar system, but there's now been a lot of science done looking at planets orbiting other stars. So we're going to start to say, if our sun behaves like this, does that apply to all the other stars? And one of the things you always see in your introductory astronomy class is what's known as the Hertzsprung-Russell diagram. These are the cool stars, low temperature over here, and they're actually the lighter stars. And the heavier stars are over here. They're hotter and more luminous. So this is temperature versus brightness, plotted as any astronomer would do backwards. So low temperatures on the right, high temperatures on the left. And that's where the stars fall in this kind of diagram. What's more important to our point is convection. Which stars actually have all the ingredients we need to generate a magnetic field? Here's the sun. We have this outer layer with convection in it. We have an inner layer that doesn't seem to convect. It just sort of sits there. If you go to the hot, heavy, bright stars, B stars for instance, that reverses itself, and most of the star just sits there. Okay? Not a good way to generate a magnetic field. Might be generating a magnetic field in the core, but really by the time you get to the surface, there isn't much magnetic field. So these stars here aren't going to have magnetic fields. They'll be bright, but they won't have this dynamo. These cooler stars, this is what I was alluding to before, have so much convection that it can actually, by the time you get to the very coolest stars, be the entire star. It's all convection zone. So this has got everything you need to generate magnetic fields. It's a conductor, and it's got lots and lots of turbulence. And so this sort of shows you the depth. This is the radius of the star as a function, again, of temperature, 4,000 Kelvin, 5,000. There's our sun, just about 6,000 Kelvin. There's a radius. That's in solar radius, so that's right at 1 solar radius. And there's the depth of the convection zone. And you can see by the time you get to a 4,000 Kelvin star, it's the whole star. By the time you get to 7,000 Kelvin, it's gone. There's no convection zone. So these are fully radiative stars. Those are stars. Oops, I think in this plot here, these hash marks show you where you see magnetic field, right there. So these hotter stars, like Vega, it's a beautiful star in the night sky, except until you learn it has no magnetic field. Blah. Some of these others are much fainter because they're cooler stars. The only ones you really see are very close to us. But they generate magnetic fields because they have convection zones. So from F stars, which are just a little bit hotter than our sun, out to M, which are the coolest that are genuinely called stars, we have magnetic fields being generated for that reason. I think I'll leave it there. I'm not going to go on. This is just revisiting. This will be all posted. Revisiting some of these basic ideas we had about how these magnetic fields saturate and then what level of activity you expect them to have. But basically, the take-home message here is with these three ingredients, which so much of our solar system seems to have, our sun, our Earth, Jupiter, Saturn, you generate magnetic fields. You need the conducting fluid, you need the complex motion, and it needs to be vigorous enough. They can create complex fields. Those fields will reverse in time. It's only when you focus in on specific parts of the field, like the dipole component, that you start to see this more regular behavior. But if you look down in the nitty-gritty, the very small-scale magnetic field, it's just very complicated. And that is also true for the Earth's magnetic field. And then I introduced the dynamo, the magnetic Reynolds number, the Reynolds number, and the Rossby number as ways of characterizing this. Oof. I think that is our 90 minutes. Any other questions before we break for lunch? Yeah. Excellent question. I will say the most common way is not to do it and to measure the effects of the magnetic fields, which I think in the next lecture we'll talk about the fact that the magnetic field is going to generate heat, and that heat actually manifests itself down in the chromosphere, and you can see the spectral lines from the chromosphere that show the signatures of that heat. That is the way they most often do it. You can, if it's very organized, you can see some Zeeman splitting, which is what we use here. But that's actually a much more difficult kind of measurement to make. The most common measurement is, I've just finished a week-long workshop on spectroscopy using big solar telescopes, and the thing they most often use is calcium signatures, but that's just because astronomers like measuring calcium. Yeah. But there's a long history of it. People have made many measurements, and they're always most often measuring the heat and then saying, what else would generate that kind of heat in the corona except the magnetic field? More heat, more magnetic field. Yeah. Actually, if I hadn't skipped over these, that's what some of these are. RHK, radiation in the calcium H and K line. Sorry. Any other questions? Yeah. Yeah, that's a good question. Yeah, one of these, where did I see?
I'll admit right now I don't know the answer to that. Sorry, we could find the answer. I know the guy upstairs who will know the answer. Yeah. Lower latitudes. Lower latitudes. I think Nick Featherstone is going to talk to us quite a bit about dynamos on stars. He will explain that. It really has to do with the organizing mechanism of the rotation interacting with the convection, and the fact that the lower latitudes are more dominant. Yeah, it tends to organize the flows in a way that generates the sunspots. Sorry, it's kind of a vacuous answer, but Nick is the one to answer that question. Not this Nick. Different Nick. Have I dodged so many questions? You're ready for lunch? Okay, I'll take some lunch. Oh, picture. Okay. And then we'll come back and I'll try to dodge a bunch of questions about the corona.